Polar molecules interact through dipole-dipole intermolecular forces and hydrogen bonds. Molecular polarity is dependent on the difference in electronegativity between atoms in a compound and the asymmetry of the compound's structure. Polarity underlies a number of physical properties including surface tension, solubility, and melting and boiling points. Polarity of bonds. Not all atoms attract electrons with the same force. The amount of pull an atom exerts on its electrons is called its electronegativity. Atoms with high electronegativities, such as fluorine, oxygen and nitrogen, exert a greater pull on electrons than atoms with lower electronegativities. In a bond, this leads to unequal sharing of electrons between the atoms, as electrons will be drawn closer to the atom with the higher electronegativity. Because electrons have a negative charge, the unequal sharing of electrons within a bond leads to the formation of an electric dipole, a separation of positive and negative electric charge. Because the amount of charge separated in such dipoles is usually smaller than the fundamental charge, they are called partial charges, denoted as delta plus and delta minus. These symbols were introduced by Christopher Ingold and his wife Hilda Usherwood in 1926. The bond-dipole moment is calculated by multiplying the amount of charge separated and the distance between the charges. These dipoles within molecules can interact with dipoles in other molecules, creating dipole-dipole intermolecular forces. Classification. Chemists classify the polarity of chemical bonds into three groups. Nonpolar bonds occur when the difference in electronegativity between the two atoms is less than 0.4. Polar bonds occur when the difference in electronegativity between the two atoms is between 0.4 and 1.7. Ionic bonds occur when the difference in electronegativity between the two atoms is greater than 1.7. Bonds can fall between one of two extremes, being completely nonpolar or completely polar. A completely nonpolar bond occurs when the electronegativities are identical and therefore possess a difference of 0. A completely polar bond is more correctly called an ionic bond, and occurs when the difference between electronegativities is large enough that one atom actually takes an electron from the other. The terms polar and nonpolar are usually applied to covalent bonds, that is, bonds where the polarity is not complete. To determine the polarity of a covalent bond using numerical means, the difference between the electronegativity of the atoms is taken. On the Pauling scale, if the result is less than 0.4, the bond is generally nonpolar covalent. If the result is between 0.4 and 1.7, the bond is generally polar covalent. If the result is greater than 1.7, the bond is generally considered ionic. Pauling considered that the partial ionic character of a bond is an approximate function of the difference in electronegativity between the two bonded atoms. He estimated that a difference of 1.7 corresponds to 50% ionic character, so that a greater difference corresponds to a bond which is predominantly ionic. Polarity of molecules. While the molecules can be described as polar covalent, nonpolar covalent, or ionic, this is often a relative term, with one molecule simply being more polar or more nonpolar than another. However, the following properties are typical of such molecules. A molecule is composed of one or more chemical bonds between molecular orbitals of different atoms. A molecule may be polar either as a result of polar bonds due to differences in electronegativity as described above, or as a result of an asymmetric arrangement of nonpolar covalent bonds and non-bonding pairs of electrons known as a full molecular orbital. Polar molecules. A polar molecule has a net dipole as a result of the opposing charges from polar bonds arranged asymmetrically. Water is an example of a polar molecule since it has a slight positive charge on one side and a slight negative charge on the other. The dipoles do not cancel out, resulting in a net dipole. Due to the polar nature of the water molecule itself, polar molecules are generally able to dissolve in water. Other examples include sugars, which have many polar oxygen-hydrogen groups and are overall highly polar. If the bond-dipole moments of the molecule do not cancel, the molecule is polar. For example, the water molecule contains two polar OH bonds in a bent geometry. The bond-dipole moments do not cancel, so that the molecule forms a molecular dipole with its negative pole at the oxygen and its positive pole midway between the two hydrogen atoms. In the figure, each bond joins the central O atom with a negative charge to an H atom with a positive charge. The hydrogen fluoride HF molecule is polar by virtue of polar covalent bonds. In the covalent bond, electrons are displaced toward the more electronegative fluorine atom. Ammonia NH3 molecule. The three NH bonds have only a slight polarity. The molecule has two lone electrons in an orbital that points towards the fourth apex of the approximate tetrahedron. This orbital is not participating in covalent bonding. It is electron-rich, which results in a powerful dipole across the whole ammonia molecule. In ozone O3 molecules, the two OO bonds are nonpolar. However, the distribution of other electrons is uneven, since the central atom has to share electrons with two other atoms. But each of the outer atoms has to share electrons with only one other atom. The central atom is more deprived of electrons than the others. Since the molecule has a bent geometry, the result is a dipole across the whole ozone molecule. Nonpolar molecules. A molecule may be nonpolar either when there is an equal sharing of electrons between the two atoms of a diatomic molecule, or because of the symmetrical arrangement of polar bonds in a more complex molecule. For example, boron trifluoride has a trigonal planar arrangement of three polar bonds at 120 degrees. This results in no overall dipole in the molecule. Not every molecule with polar bonds is a polar molecule. Carbon dioxide has two polar CO bonds, but the geometry of CO2 is linear so that the two bond-dipole moments cancel and there is no net molecular dipole moment. The molecule is nonpolar. Examples of household nonpolar compounds include fats, oil, and petrol, gasoline. Therefore, most nonpolar molecules are water-insoluble at room temperature. Many nonpolar organic solvents, such as turpentine, are able to dissolve polar substances. When comparing a polar and nonpolar molecule with similar molar masses, the polar molecule in general has a higher boiling point. Because the dipole-dipole interaction between polar molecules results in stronger intermolecular attractions. The most common form of such an interaction is the hydrogen bond, which is also known as the H-bond. In the methane molecule, the four CH bonds are arranged tetrahedrally around the carbon atom. Each bond has polarity. However, the bonds are arranged symmetrically so there is no overall dipole in the molecule. The diatomic oxygen molecule does not have polarity in the covalent bond because of equal electronegativity. Hence there is no polarity in the molecule. Hybrid large molecules that have one end with polar groups attached and another end with nonpolar groups are good surfactants. They can aid in the formation of stable emulsions, or blends, of water and fats. Surfactants reduce the interfacial tension between oil and water by adsorbing at the liquid-liquid interface. This complex molecule has several polar groups on the right side and a long nonpolar chain at the left side. This gives it surfactant properties. A micellar, the lipophilic ends of the surfactant molecules dissolve in the oil, while the hydrophilic charged ends remain outside in the water phase, shielding the rest of the hydrophobic micellar. In this way, the small oil droplet becomes water-soluble. Phospholipids are effective natural surfactants that have important biological functions. Cross-section view of the structures that can be formed by phospholipids. They can form a micellar and are vital in forming cell membranes. Predicting molecule polarity. Determining the point group is a useful way to predict polarity of a molecule. In general, a molecule will not possess dipole moment if the individual bond dipole moments of the molecule cancel each other out. This is because dipole moments are Euclidean vector quantities with magnitude and direction, and two equal vectors who oppose each other will cancel out. Any molecule with a center of inversion or a horizontal mirror plane will not possess dipole moments. Likewise, a molecule with more than one CN axis will not possess dipole moment because dipole moments cannot lie in more than one dimension. As a consequence of that constraint, all molecules with d symmetry will, therefore, not have dipole moment because, by definition, d-point groups have two or multiple Cn axes. Since C1, Cs, C-infinity HCN and CNV point groups do not have a center of inversion, horizontal mirror planes or multiple Cn axis, molecules in one of those point groups will have dipole moment.